This video looks at how well posed predictive control is when you use long output horizons. The previous video then demonstrated through examples in single argument that the use of short output horizons is likely to lead to poorly defined optimizations, that is, optimizations which do not in fact imply optimal behavior in any reasonable sense. This video investigates the contrary position of using large output horizons, and in particular we're focusing on GPC type of algorithms. In this case, the choice of the input horizon is more significant, as will be shown. Now, just a reminder, we're assuming no feed-forward information for now. Here's the first example then. You'll see we've chosen an output horizon of 50, which is quite large. And if you look at this, you'll see the predictions seem to be okay. They give reasonable behavior, and you'll also notice that if you change the weight, it has a minimal impact. Well, in this particular case, I've increased the horizon. If I increase the horizon, this error has gone down. Let's go back. You'll see, here's the error in the first example. You can see that's maybe 0.05 to 0.1, and then if I increase the horizon, the steady state error has gone down. If I increase the weight, there was lambda equals 1, and here you'll see I've got lambda equals 10. What do you notice? It's had a minimal impact. And then you might be asking yourself, is lambda actually a useful parameter? But of course, the reason why it's had a minimal impact is you've got so many steady state errors in this performance index that they have swamped everything else. If I go to ny equals 200, you'll see that the steady state error gets smaller again. So what are you noticing? That the predictions seem to be okay. In this case, if I've got a large output horizon, the predictions are matching the sort of thing that I want, and everything looks reasonable. You've also noticed that the predicted steady state error goes down as the horizon increases. If I was to go to nu equals 2, you'll see the response seems to look very, very similar, and this is the prediction. But if you look very carefully, you'll notice that the first value of the input is a bit more aggressive. So you do actually get different closed loop behavior if nu goes to 2. Now, let's compare the open loop predictions with the closed loop behavior that results. And here you notice they are actually quite similar. And now I'm feeling a lot more confident. You'll remember in the previous video, when the output horizon was small, these curves were very different, suggesting the optimization was meaningless. Here, the curves are nearly the same, and that suggests that the optimization is actually well posed. The closed loop behavior is more likely now to be due to good design, because the optimized predictions are actually overlaying the closed loop behavior that results. Different example then. You'll remember this second example had a non-minimum phase characteristic. You'll see that if you look at this numerator, but one of the poles is quite slow. With ny equals 50, the predictions aren't too bad, but you'll notice, as before, that it's giving a sort of compromise between positive errors and negative errors within the prediction horizons, but it's not too bad. If I increase the horizon, ny equals 100, again you see the steady state errors have reduced. So as I increase the horizon, the errors are getting smaller. Again, if I look at the open loop prediction versus the closed loop behavior that results, then you see they're reasonably similar. You could make an argument about, okay, the error's larger than maybe I'd like it to be, but in terms of the general trend and everything, it's not too bad. And here I've done ny equals 50. If I was to do ny equals 100, then they would be much closer together. So what we're seeing is the closed loop behavior is similar to the optimized predictions, so I'm feeling a lot more confident that my optimization is well posed if I use a large ny. Example 3. In this particular case, you remember one of the poles was unstable, and you look at this and you say it still doesn't look good. I've used a larger output horizon, but my prediction here is still basically rubbish. So in this case, even if the control law that you end up with when you iterate every sample is stabilizing, it's clear that the optimum control strategy is nonsense, given it's based on a divergent prediction, and I would not trust it. If you took the horizon up to 150, then things don't really change. And there's a little comment down here at the bottom. Because the HP and Q matrices have been made up of divergent predictions, the other problem you're going to get is the numerics will become unreliable for large NY. Here's an interesting observation though. I've taken the same unstable example, but now I've made NU equal to 2 rather than 1. And because I've done that, there's some capacity in the predictions to actually stabilize this unstable dynamic. And you'll notice over the prediction horizon, now the predictions are looking fairly reasonable. Okay, they do diverge once you go beyond the prediction horizon because of rounding errors and the like, but over the prediction horizon itself, they're looking quite reasonable and the steady state error is small. So the prediction class is good within the horizon, even though small rounding errors cause divergence in the long term, and the use of feedback would be able to correct this. Let's go on to example 4 then. Example 4, you'll remember, had some oscillatory dynamics. Now here, if I use an output horizon of 50 and an input horizon of 1, my argument's going to be, okay, the steady state's not too bad, but look at the transients. These transients are woeful. I'm really not happy with that at all. And the problem is, when you use such a large output horizon, all the focus is on the steady state, and there's no focus on the transients. If I increase the horizon even further, here it's gone to 100, and again you see the transients are still very poor, even though the steady state predictions are good. In this particular case, increasing the control horizon would be a far more effective way of getting a good response. So here you'll notice what I've done is I've increased the control horizon to be 3. And therefore this oscillation around here is far better than it was before. Some summaries then of the observations we've made. Long output horizons reduce the steady state error in the predictions, and so the long-term predictions seem to be a lot better. And this is to be expected, because if you look at the performance index, you'll notice one of the terms is the sum of the errors squared, and clearly if you make NY very large and the predictions reach steady state after n samples, then within your cost you're going to have something of the order of NY minus n steady state errors squared. And so the steady state errors are now going to dominate J, and J will focus on making sure that those are small. If NU equals 1, then in essence what's going to happen for a large NY is the control will move directly to the steady state value or close to it. And that's what you will have noticed in all these examples, that the steady state error in the predictions was small and got smaller as you increased NY and therefore increased the dominance of the steady state error. And of course the downside is you therefore were totally ignoring the transients in the predictions. So then, for a stable process, the optimal control, and this is with large NY and NU equals 1, will be close to the desired steady state, and thus, and this is the key thing, you're going to get something which is very close to open loop dynamics. You've only chosen NU equals 1. You've basically said move the input to the value which gives me a small steady state error. So the input is going to be something pretty close to a step, and therefore you're going to get open loop dynamic behavior. Where the open loop dynamics are good, then this could be an effective control law. It will give you good integral action, open loop behavior, reasonable settling time, and you can also argue that in this case the optimization is fairly well posed. However, what if the open loop dynamics are bad? For example, they're unstable, or they have a non-minimum phase characteristic, or they have oscillatory modes. Well, in this particular case, it's not so good. And if the open loop dynamics are unstable, it could be disastrous. For an open loop unstable process, a single control move, that is with nu equals 1, is not sufficient to stabilize the predictions in any sense, and so you end up with divergent predictions. Consequently, it's not possible to form a meaningful prediction close to the target, and thus any optimization is not well posed. So what I'm saying is you cannot really use nu equals 1 if you have an open loop unstable process. It will not give you a sensible optimization. If the open loop dynamics are unstable, the use of nu equals 1 can be disastrous for almost any choice of ny. Changing ny really doesn't help. And if you do end up with a stabilizing control law, this is definitely by accident and not by design, and should not be trusted. Generally then, if you use long output horizons, they seem to make good sense for stable open loop systems, and it avoids any possibility of ignoring. We remember in the previous video we noticed we're ignoring dynamics, and that caused a problem. With large ny, none of the dynamics are ignored, and that's good. If in parallel you use nu equals 1, then the optimized predictions will match the resulting closed loop behavior quite closely for stable systems, so you've now got a fairly well posed optimization, and you're quite happy. Any ignored dynamics are at steady state, and therefore there's nothing to worry about, and we're obviously not talking about unstable systems here. But here's the problem. We've put so much focus on the steady state that there is now no focus at all on the transient errors. J must consider the steady state, but we want more emphasis on the transient errors as well, because that tells us about transient behavior and performance. And what we're seeing is that if we have a large ny and nu equals 1, we can't do steady state and transients together. So ny equals small puts the emphasis on the transients but ignores the steady state, and therefore the steady state predictions can be poor, and what we showed in the previous video is the optimization is ill-posed, and you really shouldn't be doing this. If you choose ny large but keep nu to be 1, then now all the emphasis is on the steady state, and you're now ignoring the transients. So you'll see there's a sort of a shift here from focus on the transients to focus on the steady state. And because the optimization does not focus on transient behavior, then you could end up with something that is well posed or isn't well posed, depending upon whether the open loop dynamics are good or not. So for many cases, GPC is not well defined when you have nu equals 1, and that's because the open loop dynamics are not good, and therefore nu equals 1 is not good. So the optimization could be considered ill-posed, or equivalently not emphasizing the transients enough. Conclusions. We've demonstrated through numerous examples that for many cases a low output horizon and a high output horizon are both poor choices when nu equals 1. The exception is where the open loop dynamics are satisfactory in themselves, and that's why algorithms like DMC often got away with deploying a large ny and nu equals 1, because the open loop dynamics were basically satisfactory, and therefore you didn't have a problem with your transients. With nu equals 1 in general, you cannot do a systematic design that tackles transient behavior. So if transient behavior is a problem, then you can't use nu equals 1, and you might argue this is a fundamental weakness of GPC, but it's more a question of understanding what these parameters ny and nu can do for you. What we're going to do in the later videos then is we're going to start looking at what might happen if we choose larger values of nu, and what sort of values of nu we should be choosing. With high ny and nu equals 1, the optimization is well posed. And here's an interesting point. I don't say it necessarily gives a good result, but it's well posed in that the optimization results are consistent with the closed loop behavior that results. And what this means, as you'll see in later chapters, is you can imply stability. I'm not going to go and prove that now, but because you have consistency between what the optimization is telling you every sample and the closed loop behavior that results, then you're likely to get a stable loop. It might not be the behavior that you want if the open loop dynamics are poor, but it's likely to be stable.